Okay, so the next problem is about a student who's writing at her desk and her head is tilted at an angle, which requires muscle action to support it. The figure shows the three major forces acting on the student's head. We have the weight force W, which is given as 50 newtons. We have Fm, which is the force on the muscles attached to the spine, which is given to be 60 newtons, and it acts at an angle of 33 degrees from the horizontal. And we have the force Fv, which is the force of the upper vertebrae on the head. And Fv is also at an angle theta relative to the horizontal, but that angle theta is not given. In fact, the problem asks us to find the magnitude and direction of Fv so that the student's head is stationary. Note also that the problem says that all these three forces act along the line through the center of mass. So we can see that the weight force is acting through the center of gravity here. Fm is also acting through the center of gravity or center of mass. And if we project Fv, it will also go through the center of mass. So in other words, all of the forces are acting on a single point. So we cannot use net torque is equal to 0 because we cannot choose a pivot point. If we chose the center of mass, this point, to be the pivot point, then we cancel out all the three forces because the lever arm will be 0. Choosing the center of mass to be the pivot point. Well, all the forces are passing through the center of mass. Okay, so what we can use to solve this problem is the other condition for static equilibrium. Remember that there are two conditions for static equilibrium. Net torque is equal to 0 and net force is equal to 0. We cannot use net torque is equal to 0 in this problem, so we will use net force is equal to 0. Okay, so let me just redraw the problem here. Okay, you have the three forces acting on the objects, on the head. That's Fv projected towards the center of mass. We have so that's the center of mass or center of gravity. We have the weight force that's directly downwards, and that's 50 newtons. This is Fv, which is at an angle theta relative to the horizontal. And then we have another force, Fm. Okay, so Fm is pointed that way, and let me just move Fv, the label Fv here. Okay, this is Fm. And it's at an angle 33 degrees. Let me just move the label Fm to have more space. So that's 33 degrees relative to the horizontal. And Fm is equal to 60 newtons. All right, so as I've mentioned earlier, we cannot use net torque is equal to 0 because all forces are acting on a single point, which is the center of mass. And if we chose the center of mass to be the pivot point, then we eliminate all the forces because the lever arm will be 0, and that does not give us any useful solutions to work with. So we use net force is equal to 0, which is the other condition for static equilibrium to be true. Now, whenever we're working with forces, we already have learned that if you have diagonal forces, it's always useful to get the x and y components of them, so that then we will be only working with horizontal and vertical components. So for Fm, you can get the horizontal and vertical components. So this will be Fmy, or the y component of Fm, and this will be Fmx, or the x component of Fm. We can do the same thing for Fv. So we have the horizontal and vertical components of Fv, Fvx for the horizontal component, and Fvy for the vertical component. Okay, so for Fm, the horizontal or x component so it will be this side here, and if this is 33 degrees, then that's also the same 33 degrees, and we can see that the x component of Fm will use the cosine theta function. So the x component of Fmx will be Fm cosine theta, right? Or so Fmx will be 60 newtons cosine 33 degrees, and that's equal to 50.32 newtons for the x component of Fm, and the vertical or y component of Fm, which is Fmy, will use the sine theta function, so Fm sine theta. So Fmy will be 60 newtons, which is the value of Fm, multiplied with the sine of 33 degrees, and plugging everything in your calculator, you'll get Fmy is equal to 32.7 newtons. Right, we'll leave Fvx and Fvy as they are because we don't know Fv and we don't know theta anyway. That's what we want to find. But essentially, we now have the x components of Fmx, x component of Fm, which is Fmx, and the y component, which is Fmy. If I redraw my forces, just doing a free body diagram now, through the center of mass, you know that I have a weight force that's downwards. Okay, I have an Fmx to the right and Fmy downwards. Fmx and Fmy. Okay, my vectors are not drawn to scale, but I just wanted to show the directions. And Fvx to the left and Fvy that's upwards. So that's Fvx to the left and Fvy that's upwards. Okay. So remember, when you're doing just net force is equal to 0, you it's not so important where the forces are located at, and so you can just draw this simplified free body diagram of all the forces originating at a single point. It's when you do net torques that the location of the forces is important, because you need to consider the lever arms, or the distance between the force and the pivot point. Okay, but by drawing the simplified free body diagram, I can clearly see the directions of the forces, and so I can know whether it's positive or negative. So we use the usual convention that upwards means positive y and to the right means positive x. Right, so if I now get the net force along the x component, or along the x-axis, or along the horizontal, then I can see that Fmx is positive and Fmvx is negative. So I have Fmx, the x component of Fm, minus Fvx. Okay, and the net force should be equal to 0. Okay, so the net force along the x-axis should be equal to 0, so that all the forces along the x-axis cancel each other out and add up to 0, and we have equilibrium, static equilibrium along the x-axis. So Fmx minus Fvx should be equal to 0. And that allows me to solve for Fvx, which I don't know. Rearranging this, Fvx should just be equal to Fmx. And you can also see in your free body diagram, there are only two forces along the x component, or x-axis, just Fmx to the right and Fvx to the left. So these two forces along the horizontal should balance each other out, and so Fvx should be equal to Fmx. Fmx, we have already solved here. Fmx is equal to Fm cosine theta, or Fm is 60 newtons times cosine 33 degrees. So Fmx is 50.32 newtons. So Fvx, the magnitude of Fvx, should also be equal to 50.32 newtons. If you were to put the direction, of course, you know that it's to the left. Okay, or if you wanted to specify Fvx as a vector, you can put Fvx is equal to negative 50.32 newtons. But for the magnitude, it's 50.32 newtons just for the magnitude. Again, this negative sign means that it's to the left. Right, now we can do net force along the y-axis. And the static equilibrium condition says that the net force along the y-axis should also be equal to 0, so that there's no motion along the y, or along the vertical. So we go now to our free body diagram. You can see there are three forces along the y-axis, Fvy, W, and Fmy, and they should all balance each other out, meaning Fvy should balance out with W and Fmy. That means that Fvy minus W minus Fmy should be equal to 0, or you can just say Fvy should equal the sum of W plus Fmy, right? The force that's pointing upwards should equal the total force that's pointing downwards. Right. So we're given the weight force, which is 50 newtons. So W is given 50 newtons, and we've solved Fmy earlier. Fmy is equal to Fm sine theta, so that's 60 sine 33 degrees, which is 32.7 newtons. Right, so we have Fvy is therefore equal to 82.7 newtons. Okay. Right, looking at our diagram here, so FVY is pointing upwards. You see how FVY is pointing upwards. So the direction of FVY will be upwards, or that will be positive. Right, so we now have these values, FVX and FVY. These are the components of FV, X and Y components of FV. In other words, you have FVX is negative, so that's pointing to the left. Let me just redraw a straighter line. So that's FVX. Okay, and FVY is positive. FVY is pointing upwards. Right, so the resultant force FV is the hypotenuse of this right-angled triangle. And that will be theta that we want to measure. So we know that if you have a right-angled triangle and we know two of the sides, the horizontal and vertical sides, then we can solve for FV, the hypotenuse using Pythagoras theorem. So that's FVX squared plus FVY squared. Right, so that's square root of 50.32 newtons. And you can put the negative sign. Just make sure that you bracket including the negative sign when you do the calculator squared. And then you have 82.7 newtons for the Y component squared. Okay. If you plug in the numbers in your calculator, you have FV is equal to 96.79 newtons, which is about 97 newtons. So that's FV is about 97 newtons. Now for the angle, we do tan theta is FVY divided by FVX. Okay. So you go negative 50.32 divided by 82.7 for tangent theta. Right. Theta will be the arctangent of 50.32 divided by 82.7. Oh yeah, I got it the other way around. Yeah, I got the values the other way around. Our FVY is actually 82.7. So FVY is 82.7 divided by FVX is minus 50.32. Okay. So theta will be arctangent of 82.7 divided by 50.32. Okay. You will get a negative answer for the theta, which is negative 58.7 degrees. Okay, that just means the negative sign just means that you measure, if you measure the angle in the anti-clockwise direction, in the clockwise direction relative to the horizontal. So this is your angle theta, 58.7 degrees relative to these FVX that's pointing to the left. But if you measure measuring the angle from the positive x-axis then your angle will be 180 degrees minus 58.7 degrees. So that will be 121.3 degrees. Right. So if you measure the angle relative to the positive x-axis, this is 121.3 degrees. I think the convention we're using is that we measure the angles relative to the positive x-axis. Yeah, so it will be 121.3 degrees. In your calculation, you got negative 58.7 degrees, which means that that negative 58.7 degrees was measured relative to the negative x-axis from where the FVX is. And FVX is pointing to the left, and that's why you go clockwise when measuring relative to the negative x-axis to the FV, and that's why that's a negative 58.7 degrees. But yeah, but to remove ambiguity, we measure our angles from the positive x-axis, and so it's this angle here, and that's why we did 180 minus 58.7 degrees, and so that's 121.3 degrees. All right, so there you have both the magnitude of and direction of FV. Magnitude being 97 newtons and direction being 121.3 degrees measured from the positive x-axis.